Hey Pete, I'm going to attempt to answer a couple of your questions using this little screen recorder tool. I apologize if this feels very Khan Academy-ish, and I apologize. The handwriting with the stylus is just awful, so please bear with me. But I wanted to go ahead and just attempt to address a few of the questions that you had expressed. So the first one was you had mentioned that you weren't sure how to convert between radians and degrees, or something about what the relationship was. So really radians and degrees are just different ways that we can describe basically the angle that makes up a circle or parts of a circle. So you can think of it similar to how we convert between metric units and standard units of measurement. So like for example, in the US, we measure obviously in feet. Over in Europe or literally any other place in the world, they measure in meters. Okay, so if I wanted to know, or if I wanted to convert a number, between feet and meters, the conversion is that there are three. Oops, I need to put my pencil on. Sorry, there are 3 feet for every one. I told you the handwriting was bad. 1 meter. So this is kind of how basically the ratio that we would use to convert between feet and meters if we needed to. And degrees and radians are basically the same thing. So the relationship between degrees and radians is that 360 degrees, which is a full circle, okay, 360 degrees is equal to 2 pi radians. Okay, you can also think of this in terms of a half a circle, and actually half a circle is what's commonly used just because it's a little bit more of a simple ratio. So 180 degrees, 180 degrees, which is exactly half of a circle, is just pi radians. Okay, so for example, if I told you, let's say that we had pi over 2, or 45 degrees. Let's say that I had, 90 degrees. Let's do 90 degrees. That's an easy one. So let's say that you had an angle that was 90 degrees. And I said, I want to know how much is that in radians. You would just take the 90 degrees and you would multiply by this one of these relationships here. Okay. So I would multiply by pi over 180. And if you remember, we put the degrees on bottom because we want the degrees to end up canceling top and bottom. So I have an answer that's in radians. So then I just kind of plug that into my calculator and don't include the pi. And the reason why we don't include the pi is because, as you can see over here, we usually write our answer in radians in pi, or like we leave the answer in terms of pi. So if I take 90 and just divide it by 180 flat out, that gives me 1/2, right? So this answer then, oops, that's a 1, hold on. So this answer would be 1/2 pi, which we more commonly would say pi over 2. So the way that we say this then is that 90 degrees is equivalent to pi over 2 radians. And again, it's this ratio that allowed me to convert from degrees to radians. And I didn't have to do pi over 180. I could have done 2 pi over 360. But then obviously I would have a 2 in the numerator and I'd have to get rid of that. So sometimes using just 1 pi makes life easier. Okay, so that's kind of the gist of how we convert from degrees to radians. Okay, so now I want to get to your next question on, okay, how do I use that to find arc length? So let me get a new page here. So this is the problem that I saw in Khan Academy in one of the practice sets. I don't know if you've seen this problem or if yours looks similar. I'm hoping that it does. So we have a couple things going on here. So we have S is our arc length. Okay, so arc length S. Okay, and we have our radius, which is 5. So S, we don't know. Our radius is 5, and it's just 5 units. We don't exactly know if it's centimeters or inches or whatever, but that doesn't matter. And then our angle in radians, it tells us, is 0.4. So I'm going to use theta. So our angle in radians is 0.4. Now you can see here that they're not using pi. The reason for that is because it's such a small segment of the circle that this is really just a fraction of pi. So using pi isn't really very helpful at this point. I hope that makes sense. If we were doing like a half of a circle or 3/4 of a circle, that's when using pi is a little bit more relevant. But when we get to really, really small decimals like this, we've gone smaller than pi. So at that point, it doesn't really make sense to use it. Anyway, sorry, I'm probably just confusing you. Anyway, so this is what we have. Okay, so let's talk about how these things are related, because I know that you had mentioned that they don't really give you a good formula for this. But let's talk about a formula that you already do know, hopefully. So hopefully in your head, you know that if I were to take the circumference of a circle and divide it by its diameter, that relationship is pi. Now, maybe you didn't know that, but in theory, that was something that was supposed to be in your middle school curriculum. So I don't know if you learned that or not, but that is a relationship that exists among all circles. So I could take a cookie, okay, that's a circle, an Oreo, for example. And if I measure the circumference of that Oreo, and I measure the diameter of that Oreo, and I divide the circumference by the diameter, I'm going to get 3.14 on my calculator. I'm going to get pi. It's a universal relationship among circles, okay? But then you might be asking the question, okay, Mrs. Zavaker, how does this help? Okay, well, remember that this is about arc length. And arc length is just, if we think about it, a segment of a circle, or a segment of a circumference. So the arc length is just, it represents just a part of the circumference, or think of like an incomplete circumference, okay? Now, obviously, in our problem, we didn't have diameter. We were given radius, but luckily, there's another relationship that I'm hoping you know of. That is that the diameter is made up of two radiuses back to back, right? So in other words, I can rewrite this equation to basically relate the circumference to the radius. Oh my goodness. Writing with a stylus is seriously the hardest thing ever. Okay, so instead of dividing circumference by diameter, another way that I could write this is I could divide the circumference by 2 of the radii, right? Because again, 2 times the radius is the same thing as the diameter. So all I did was I swapped out diameter for 2 radius. And again, I hope that makes sense to you. Okay, but again, you know, I'm trying to solve this problem, and this problem just has 1 radius. It doesn't have a diameter. So maybe there's a way that I can kind of break this down even further to just relate the circumference to the radius without this 2 there. So how would I get rid of that 2? Well, if I take my equation, circumference divided by 2 times radius, if I take and multiply both sides by 2, okay, that's going to eliminate the 2 on this side. So now the nice thing, and what I've basically just accomplished, is now I just have the circumference related to 1 radius, not 2, but 1. So the circumference divided by the radius is equal to now 2 pi. Okay, and if you remember from back on our other page over here, where is it? We talked about 2 pi is a full circle, right? Because 360 degrees was 2 pi radians. So essentially what I'm saying now is that if I have a full circumference and I divide it by my radius, I'm going to get 2 pi radians, which represents the full amount of radians of a circle, which makes sense because, again, if I have the whole circumference, that means I have a whole circle. So I would expect all of the radians to be there in a full circle, right? But the issue that we have with arc length is that we don't have a complete circle. We don't have a complete circle. We have like a partial circle, or a circle with a chunk that's been taken out, right? So if I kind of go over to another page here, I'm sorry, I can't write much on one page. So again, I'm left with circumference divided by radius is equal to 2 pi radians. So this again is if you have a full circle. But if I'm thinking about arc length, something like this, okay, like what was in my example, I don't have a full circle. I only have a part of a circle. But the nice thing is this relationship is still going to change. Just kind of what we call each piece is going to change. So now instead of a full circumference, I have arc length, which again, arc length is just a part of the circumference. And because it comes from the circumference, because arc length is a part of the circumference, it maintains this relationship between the radius and no longer 2 pi, because remember 2 pi was if I had a full circle. Well, I don't have a full circle. Okay, I have this little partial circle. So instead of setting it equal to 2 pi, it's just equal to some number of radians. And actually, instead of writing radians, I'm going to write theta. Sorry if that's confusing. It's equal to theta, like that. So really, this is the relation. These two are the exact same relationship. It's just that in this one, we're talking about a full, complete circle. And in this one, we're talking about a chunk of a circle or a small segment of a circle, if that makes any sense. Okay. So again, to kind of simplify this, I believe it was S. S was the variable in our example. So the arc length is S. So the arc length divided by the radius is going to tell us the number of radians. Okay. Now, if I remember correctly, in the example that you were given, it wasn't actually radians that you were solving for. I believe you already had radians. So let's flip back here really quickly. So we have S over R equals theta. That was kind of the, oops, jeez. That was the relationship that we came up with. That's still bad. You know, whatever. You know what I'm talking about. But again, I can rearrange it. So what am I solving for? I'm solving for S. I'm solving for the arc length. So if I want to solve for arc length, obviously right now I've got arc length divided by the radius. I can just move the radius to the other side by multiplying. Whoops. Try again. Wow, that's a times. Just go with it. Okay. So if I multiply both sides by the radius, those guys cancel, and I'm just left with the arc length is equal to the number of radians, theta, the number of radians, times the length of the radius. Okay, so now I can just plug in what I know. So in this case, S is equal to this decimal point, 0.4, and I'm going to put it in parentheses. I'm sorry, I'm going to attempt to put it in parentheses because I'm getting to the bottom of the screen here and it's getting really hard to write. 0.4 times the radius, which is 5. And that's just a plug and chug. You can just plug it into your calculator, or you can say what's 40% of 5? Well, that is 2. That is 2. So your arc length, in this case, is 2. Okay? So, listen, I know that was kind of a lot. I am really drawing on a lot of background information here that I'm really not even sure if you have, because again, I'm not sure what your middle school curriculum, what they were able to cover. But I'm hoping that this gives you a little bit more of an understanding. If not, let me know, shoot me an email, and we can try to do a video chat tomorrow, maybe with mom or dad on the call. And we can kind of go through a couple more examples if this didn't quite do it for you. Okay, so just let me know. Thanks, bud. Good luck.